Okay, so it's my pleasure today to introduce Professor José Príncipe. Thank you, Professor, for accepting this invitation to talk to us. José Príncipe hardly needs an introduction, but I am honored to say a few words.
Yeah, just a few words. Take it light.
Briefly, José Príncipe is a distinguished professor of electrical and computer engineering and biomedical engineering at University of Florida, where he teaches advanced signal processing, machine learning, and artificial neural networks modeling. He is the EKIS professor and founder and director of the University of Florida Computational Neuroengineering Lab now. Okay, he has been working, and his main interest is processing of time-varying signals with adaptive neural models. He has been chair of many international and well-known societies. He has published more than 1,000 papers and has an H index of 101. He directed 108 PhD dissertations and 65 master theses. He has also published several books. Thank you very much for accepting our invitation, and the floor is yours.
Yeah, thank you very much for the introduction. It's a pleasure to be here and talk to you about some work that I've been doing for quite some time related to information and deep learning. And the title of the presentation is Dynamics of Information and Deep Learning. I'm going to speak in English, as you can see, and if you have questions, please interrupt, or we'll have questions at the end. So, I would like to acknowledge a very large group of students that helped to make this possible. And the outline of this talk is really concentrated on the importance of information in machine learning that is often forgotten. Information theory showed to us that there are two basic descriptors in information theory, entropy and mutual information. And it turns out that these two descriptors have a higher specificity than the PDF moments that we normally utilize in statistics to describe the probability density functions. I have done quite a bit of work on using principles of information theory to train learning systems, and I'm going to briefly review this part early on in the talk, and then I'm going to show applications of more advanced descriptors or algorithms to estimate entropy and mutual information in the second part of the talk. That is going to apply these descriptors to understand the dynamics of learnings and the selection of hyperparameters in deep neural networks. So we have to define, talking about information theory, we have to define what is entropy. And the idea is very simple. Not all random variables are equally random, as I tell my students. What seems strange, because if they are random, why they are not equally random? But the idea is very simple. Suppose that you have a peaky distribution, as you see in the right part of the slide. And if we do realizations from this random variable, you see that the number of zeros is going to be much more than any other value in the domain. However, if the probability density function is flat, as also in the figure at the right, if you do realizations from this random variable, you are going to have equally likely values in the domain. So that means that the sequence of realizations of the second random variable is more random than the first. And it turns out that the the mathematical definition of entropy exactly captures this concept in a very, very specific manner. This was proposed by Claude Shannon in the 40s, and I have the two equations that on the left you see that the entropy of the random variable x is the sum over the probability density function of the log of p of x for discrete random variables. And on the right, you see the equivalent equation when the random variable x is continuous. So the issue is that Shannon, armed with these two definitions, he did wonderful things. And I would like to start by showing the optimal design of communication systems. It turns out that to design an optimal communication system, you have to know the probability density function of the source of the messages and also the probability density function of the signal that is added to the transmission from the emitter to the receiver. So once you have the information about these two random variables, then Claude Shannon proposed basically two important theorems. One that compresses the source X into a reduced size variable X prime or X hat. That is the compression theorem. And then the second theorem is the error correcting theorem that is also called channel capacity theorem, that tells you that if the data rate in the communication channel is less than the maximum of the mutual information between the codes and the output of the receiver, then you can recover without an error as small as you want the source information. And so this really kind of self-organizes, is a system that self-organizes itself to operate, perfect recovery of information. And of course, we wish we could do this when we are designing machine learning models to optimally extract information from our input in the code of the neural network or in our mapping function. But we cannot do that. And the reason for that is really we do not have full description of the statistics of the input data. This slide kind of tells you what is a machine learning model that operates directly with input data. I call this an information filter. And you have basically three components. You have an adaptive system, that means a mapping function, that receives from the world pairs of data, xi and dsub. And we use one of the pairs, xi, as the input to the mapping function, and we use the desire as the target for the output of the model that is here, that is called y sub I. We create an error, and then we put the cost function on the error, and this is the second building block of an adaptive model. We have to have a cost function that rates the quality of the errors. And after that, we are going to try to change the parameters, the free parameters of the mapping function with the learning algorithm. Notice that this feedback is closed loop. And so the human is not in this feedback loop, as you can see. And that means great things because we can compute, we can update parameters at the speed of our computers. Okay, so we are out of this loop, but of course we design or we select the adaptive model, the cost function, and the learning algorithm. Normally the cost function is based on the mean square error criteria. That is really the square of simply the error. But we can also think of using an information criteria to substitute the mean square error. And the obvious answer for someone that knows information theory is to exactly use the definition of entropy. And the role would be to minimize the entropy. But we have a technicality that needs to be corrected because the minimum error entropy is scale invariant. And so we have to add an output, a parameter to our mapping function that centers the error at 0. But with this little modification, we can come up really with a way of including in the parameters of this model, including information that is contained in the error. Just to give you a brief overview of adaptation, obviously adaptation is an optimization problem, as we all know, but I think it's important to hear what Tsipkin, in his very nice book called Adaptation and Learning in Automatic Systems, published in 1971. Most of you in the audience probably were not born in 1971, but it's good to read this book to understand really what was Tsipkin's ideas about learning and optimization. So he defined 3 possible problems for learning systems. First one is where the deterministic function, the mapping function that we want to optimize is deterministic. And in this case, this is the very well-known Pontryagin maximum principle that was proposed in the 50s. However, most of the times, the mapping function over the domain of X is stochastic. And in that case, we assume that the statistics don't change. And with this assumption, we have an optimal solution given by the Hamiltonian-Jacobian-Bellman's equation that is so very well known in control theory. But also, Tsipkin also told us that this is fine, but when we have an online model, we really don't have the statistics of the data for us at every sample. And more than that, the statistics may change with the time series or the signal source. And therefore, what we have to do, we have to do 2 things. We have to estimate the statistics online and then compute the expected value of the function to optimize the performance with respect to the Hamilton-Jacobian equation. So this third point is really the most difficult of them all, and we are still struggling with it because we don't have optimality under these circumstances. And so my work on information theoretic learning really is a step towards this third problem, and I'm going to briefly describe the fundamental issue that we have, that I already mentioned, is that in machine learning, we don't know the statistics of the input data. So we have to estimate them from data. The problem is that entropy defined by Shannon is difficult to estimate. And in my work, I've used another definition of entropy called Rennie's entropy, that in fact is a family of entropies parameterized by this parameter alpha that is a real positive number. And the definition of Rennie's alpha entropy is 1/1 minus alpha log of the sum of the alpha power of the probability density function for discrete random variables, or the integral for continuous random variables, as you can see in the slides. So there is a very interesting difference with respect to Shannon, is that the log appears before the integral, before the sum. And it turns out that Rennie showed that when alpha tends to 1, effectively Rennie's entropy of alpha equal 1 becomes Shannon. And so Shannon is a special case of this very large family of distributions. And it turns out that we have to understand, since we have a parameter, we have to understand the value of this parameter. And let me go to the discrete case that is easy to explain. And let's assume that we have a simplex, in this case with two random variables, P1 and P2. And obviously in the simplex, all the joint probability density functions of P1 and P2 are located in the line, right? And if we select a certain distribution, joint distribution, we have a point in this line, and we can compute the distance between this distribution and the origin of the simplex. And when we do so, we have the possibility of using many different norms. And so the alpha in Randy's entropy is nothing but the selection of the norm that we use to estimate the distance between the joint distribution in the simplex to the origin. And we call this the information potential. And it's just, as you can see, is just the argument of the log in the expressions above that I have, that I call V sub alpha. And I'm going to call V sub alpha information potential. And now let's see with this definition, with alpha equal to, so I'm going to use a square norm, a quadratic norm to compute the distance of the probability density function to the origin. And this is what is called quadratic Renyi's entropy. And so what we would like to do is to minimize the entropy of instead of minimizing the mean square error, because entropy is associated with variance, so what makes sense is really to minimize the mean square error, the entropy of the error variable in the block diagram that I showed to you. But instead of taking the log, since log is a smooth, a monotonically smooth function, I'm going to drop the log and just work with the argument of Renyi's quadratic entropy, because this does not change the location of the optimum in the data space, in the error space. And so basically what we need to estimate then is just the integral of the probability density function of the error square. As you can see immediately, this is nothing but the expected value of the probability density function. And so when I'm maximizing the information potential, I minimize the error entropy. And this basically means that what I'm doing is when I change the parameters of this model in the block diagram, I'm going to change the distribution of the errors. And the best possible value is when all the errors converge to 1 point. That means the error PDF becomes a delta function. And so basically, you see that minimization of the error entropy associated effectively in creating distributions of the errors that effectively are very picky, okay? And we can do that, as I said, by putting an extra parameter in our mapping function to guarantee that error distribution appears at the origin. Because when I do the maximization of the information potential, I'm not fixing the point in the space of the error where the PDF is going to pick. Okay. All right, so we have now understanding of what is the cost function that we want, and now we still have a problem because the expressions that I told you still work with the probability of the error, the PDF of the error. And so since I have samples from the data, I don't have the information about the PDF, but I can estimate it, using, as we know, in the kernel functions in PDF estimation. This is an old work that started with Rosenblatt and Parson. Now we call this method Parson estimation or Parson window estimation. And the idea is very simple. The idea is we are going to estimate P of X, and I'm going to, the hat tells about the estimator, right? And it's is going to be just the sum of a kernel function that you can think is a positive definite function, and basically that is the only requirement for the kernel function for this application, but we can think that this kernel function is a Gaussian, that is symmetric. But even if it's non-symmetric, there are kernel functions that can be used, in fact, with some advantages. But basically what I'm saying is I'm going to place a Gaussian function over all the samples that I collect from the real world, and I'm going to add these Gaussian functions, okay, and divide by the number. And this gives us an estimator of the probability density function. It turns out that there are very nice properties about this estimator, that were proved by Parson, because the estimator is statistically efficient, and we can guarantee, the convergence to the optimal solution provided of some conditions. But we also know that this estimator is good. Is a good estimator for when the dimensionality of the input variable x is small. I would say small here is less than 20 dimensions. So armed with this, now that we have this estimator, how can I estimate the Renyi's entropy directly from my samples? It's very simple. I just need to substitute p square of x by the estimator square, okay? Use the properties that the integral is a linear function, so I can interchange the order of integration and summations. And I have this beautiful thing that if my kernel is a Gaussian, this integral between the Gaussians of x minus x sub I and the Gaussian of x minus x sub j effectively can be computed analytically as the Gaussian between the differences of the samples with a change in kernel size, the width of the Gaussian. So this is an exact result. And as you can see, I can estimate directly from data Renyi's quadratic entropy. Okay. And so this really tells you the reason why I think that the Renyi's alpha entropies are so nice to work directly with samples when we want to estimate entropy and major information. But I have to note that this estimator has a double sum, so the complexity is n squared on the number of samples, and has a free parameter. Okay, so this free parameter is exactly the width of the kernel that we are using, and that needs to be estimated from data with cross-validation. So this is really the framework. Now I'm able to effectively estimate from data, a cost function that minimizes the entropy of the error. This, we don't need the algorithm, the logarithm in Renyi's entropy, as I told you. I also like to say that this alpha parameter, for someone that works with Shannon entropy is kind of it seems a bug, right? Because entropy should be always the same, right? And it's true that this methodology has a free parameter that adapts it to many other different data sets, what is good. And here, I'm just interested in finding out where the location of the minimum, I'm not, or of the maximum of the information potential. And so I don't really care what is the value that I have at the moment, at the maximum or the minimum. I just want to find out where it exists in the space of the data. The other interesting thing is that this estimator with Gaussians, gives us an interpretation of samples in a reproducing kernel Hilbert space that is very nice, because it gives us each data set sample becomes a function in the Gaussian space, and it turns out that the data set itself creates an information potential over this space that really is associated with the probability density function of the data. And this analogy that I'm kind of hand waving for you can be proved exactly by the theory of statistical embeddings in the reproducing kernel Hilbert space. So basically, since if I use a gradient descent approach to train the parameters of my model, as we normally do in machine learning, this means that I have to compute the derivative of the cost with respect to the parameter, and this becomes an information force. So basically, you can think that in terms of information potential and forces, the samples in the space are going to move according to the algorithm that I want to minimize or maximize. This slide is complicated. Probably I'm not going to spend too much time on it, but for those of you that are interested, it just tells you how you can actually implement the minimum entropy by in a learning problem. The equations are for the linear model, but with a slight modification, you can apply this also to nonlinear models. And I'm not going to talk about these details. I'm just going to show you that, so this can be integrated exactly in backpropagation. And this is an example of maximizing the output entropy. And you see that the sample size, the samples, when you maximize the output entropy, you basically just you do a coverage of the space with your samples, what I think is an interesting idea. We can apply also the same methodology that I explained for entropy to mutual information and to Kullback-Leibler divergence, in fact, Renyi's divergences. But again, this is a lot of more detail on the mathematics, and I don't want to get into the details, just tell you that the same basic methodology that I explained to compute Renyi's entropy can be applied to compute Renyi's divergence, and even other forms of divergence like Cauchy-Schwarz and others that appear in the literature that are easier to estimate. I'm going just to now give you some ideas of how can we extend this estimation of entropy and mutual information for dimensions above 20, as I said. The method that I'm going to explain to you has been already tested in dimensions up to 1,000 with very interesting results. And so I think that this is the methodology that you should use if you are interested in utilizing very large dimensional systems. The idea is, I already mentioned it, is we move the data to a reproducing kernel Hilbert space defined by the kernel function, for instance, for the Gaussian. That will be a Gaussian kernel that defines a reproducing kernel Hilbert space. And what we are going to do is we are going to work with the grand matrix of the data. The grand matrix of the data is the matrix of the Gaussians on pairwise samples. So this is a very large matrix, right? Because if you have 1,000 samples, this will be, a million elements in this matrix. But it turns out this matrix is positively definite, and if we normalize it properly, it becomes an Hermitian matrix. And so what we did in this paper that was published in the Transactions on Information Theory is that we redefined the Renyi's alpha entropy as exactly 1 over 1 minus alpha, the log of the eigen decomposition of the normalized emission matrix. So basically what you have to do, you have your grand matrix, you compute an eigen decomposition of this matrix, and you just raise it to the power alpha, right? And basically what you have is your definition of Renyi's alpha entropy. It turns out that we can also use this S sub A of A to compute joint entropies. Notice that the symbol means another NMR product of elements between these two matrices. So if I have two data sets, X and Y, I have two gram matrix A and B, and so I work with the matrix A and B and compute the ratio of the NMR product of A and B with the trace over the trace. And we can also define mutual information using this S sub A of A in the form that is included in the slide. We can estimate it to more than 2 dimensions. Okay, so we can compute, effectively entropies and mutual informations amongst multiple dimensions, and we can define also co-information. That means the multivariate mutual information in the elements of the set in the way that I present here in this formula. And so all the formulas now that we have seen that have entropy and mutual information can effectively also be written in the form of this estimator in the reproducing kernel Hilbert spaces. I'm not going to go into more details, but this is just for your information. We can rewrite co-information in terms of the S operator. We can also express total correlation in terms of the S operator. I can compute mutual information between groups of variables also with the S operator. And so this becomes then useful, very useful in machine learning. So this is kind of the theory part. And now I'm going to show you how I can use the S operator to understand the learning in deep neural networks. Of course, we know the advantages in terms of mapping accuracy of the deep neural networks, but of course the issue is this becomes a black box because it's so complex, the architectures are so complex that we really don't know well how to optimize the performance of this system. And the idea is to see if ITL can help us exactly understand the inner works of a neural network while it is training. Of course, neural networks, deep neural networks are difficult not because of the elements of the nonlinear processing elements or units in the network, because those we understand very well what they do. If you think about it, they just do sum of products, just like in the linear model, but they are followed by a nonlinearity. And this nonlinearity has the big advantage that makes the output, lie outside the span of the input data. And this is really the big advantage of neural networks, is that we can get better approximations than than the linear model can, because we rotate the spaces in such a way that they get closer and closer to the desired response, where the error becomes the smallest. I already have explained this many years ago in this book that I wrote, Neural and Adaptive Systems. But the issue is that we still don't, the difficulty is to make sense of the learned projections. Okay, so the difficulty is how can these simple ideas be brought to bear in the understanding of the system. And so we were very pleased when we read this paper by Tishby, where he proposed the information plane to analyze pairwise mappings between layers of neural networks using mutual information. So the information plane that is basically, as the figure shows here, is a graph between the mutual information from the input of the model up to a certain layer T in the neural network as the x-axis, as a function of the mutual information between the same layer and the output of the network. Okay, so this gives you a two-dimensional view of the changes in mutual information up to the particular point in the network that you like to analyze the performance, and with respect to that same point with respect to the output of the model. Okay? So in order to apply this concept, we have to make some assumptions. And the first assumption is that the neural network has to be feed-forward. I still don't know of any way of applying this idea to recurrent models because they are no longer Markovian. But it may be possible, but maybe some of you can solve this problem because mutual information has been also applied for signals for channels with feedback, and the recurrent neural network is also a system with feedback, so that may be possible to move beyond this restriction that I'm presenting here. Okay, and so basically, of course, the neural network is also a much more complex model than a transmission system. And so we have to really see that there are two flows of information in the neural network that I'm sure all of you that know machine learning and backpropagation understand. So you have a flow from the input to the output of the model, right? And then through backpropagation, what you do, you compute the errors at the output and you backpropagate the errors through the network. So basically you have two flows of information. The flow of activations and from X to Y, and the flow of errors from Y to X, okay? And in order for this methodology to work, these two flows have to obey the Markov assumption, or the data processing inequality that some of you that know information theory may be familiar with. What the data processing inequality means is that there is always a decrease in mutual information when you have successive layers. That means when you send an information from X over Markov chain, the first layer, the mutual information from X, between X and T1 is always greater than the mutual information from X to T2, and so on. Okay, so that means that the data processing inequality tells you that the mutual information is equal or always decreasing across layers. Okay, so if that is the case, we thought, okay, so we have these estimators, high dimensional estimators, and so we decided to see if we could verify experimentally these properties. And this is an example of a five hidden layer MLP trained on the MNIST. And as you can see, effectively, in blue you see the mutual information decreasing across iterations, across layers, as you can see in blue. And you also can see that the errors have the opposite decay. They start very high, the mutual information very high because you are computing mutual information of the error with the top layer, the output of the top layer, and so you see that this has the highest information, and then the mutual information decreases of the errors to the front layer. This is known, but this is a very interesting thing that we can compute how much the decay of the information is in a trained model. Now I'm going to go to a more complicated DNN, that is called the stacked autoencoder. And what is interesting is in stacked autoencoder, stacked autoencoder looks like a communication system because I have X at my input and I want to recover X at the output of the decoder, right? And so, but the problem is you have a bottleneck layer that is called Z, and that is dimension much lower than the other two. And if I compute the mutual information between X and the layers in this autoencoder, you see that I have a very strange curve because now the curve is kind of a convex. That means it decreases up to Z and then increases from Z to the last layer. But notice the autoencoder, right? The desired response of the autoencoder is equal to the input. So this makes sense, right? But it seems that it's not, in the same form. But of course, we understand that the reason is this analysis does not differentiate between the error and the input, but the error in this case, the desired response in this case is also the input. So the error also contains information about the input, right? And so in order to disentangle these two things, what we computed the conditional mutual information of X with respect to a certain layer, T2, given the error in the previous layer. And so effectively, when we do this conditional, what you see is effectively, we see again, as we could expect, that the conditional mutual information in the stacked autoencoder also decreases with the layers as we expect. Okay. I don't have more time if I want to have 15 minutes of discussions, but I just want to give you a very interesting. So I'm going to summarize the next slides, but the first two hypotheses I already talked about is not interesting. The third hypothesis is what I think is interesting for the autoencoder because we have the bottleneck layer. And the bottleneck layer projects the input data to a subspace. And the question is that if I project the input layer to a very small subspace, I can have entanglement of I can destroy the structure of my input data, right? And of course, if I'm careful in selecting the number of layers and the number of elements in the Z layer to higher values, then I can still preserve the information of the input, right? So this third hypothesis means that there exists a bifurcation of the performance of an autoencoder between two regimes when the bottleneck layer is too small to accommodate the intrinsic dimension of the input data, or when the output of the middle layer has enough degrees of freedom to still represent input data. What is interesting is that in this plot, I would like to show that when and this was done on I think also Fashion MNIST, MNIST only. This is MNIST data. So I'm training the autoencoder for MNIST. The number of the number of neurons in the bottleneck layer is 36, and what you see is that between the input of the output layer and the output of if I compute the entropy of the bottleneck layer in black, you see that you have an increase of entropy through training, and then the entropy decreases again. Another interesting thing is to show that even in this case that where the first hidden layer is a dimension 1,000, I don't gain any information by putting 1,000, right? Because as you can see here, the mutual information caps at a certain value. If I now select the dimension of the bottleneck layer to 2, notice that the described behavior of the entropy does not occur anymore. The entropy always increases. And this is exactly that shows that effectively you have entanglement, so that means you are going to distort the input data structure, and effectively you are not able to train the model appropriately. These curves are very interesting, And this is, so let me explain what these plots are. These are the information planes for the 4 layers of the stacked autoencoder across iterations. So in the blue to red, you see the number of iterations. And what you see is when the bottleneck layer is 2 processing elements only, the entropy, the meter information in the input space, in the information plane are just lines that change slope, but they are simply lines. But when you start increasing the size of the bottleneck layer, you see that it starts with the deep layers. You have this return of the mutual information in the information plane, and for k equals 36, you see that all the layers have the same behavior. That means that mutual information, increases and then it decreases after a certain point. And this is a very interesting behavior that was not expected in the beginning, but now we understand why it works. I'm not going to go. This is a very interesting plot that I would like to just put an appointment. Give you the 30-second message of this plot. Notice that the left figure is the mutual information. The right figure is the classification accuracy. And it turns out that the point of maximum generalization is associated exactly with the peak of the entropy of the bottleneck layer. And this is a very interesting thing because I have the peak of a distribution that tells me where is the best generalization. And so this is something that we are not the only ones that verified this, but I think that this can be a very important point to end the training of neural networks. The last thing that I like to talk about is this understanding residual networks or ResNets. The question is the following: in the ResNet idea is really you short circuit some layers of this very long network, right? But the question is, what should be the short circuit? And what type of function shall I use for the short circuit? And the author said, well, the one that works better is just a short circuit with the value of 1. That means just put 1. And why is 1 so nice? And it turns out that 1 is nice because if we think of this in terms of the data processing inequality, what you see is that the only case where the mutual information does not decrease in a layered Markov model is when the transfer function maximizes mutual information. That means the mutual information has to be 1. Okay? And so that is really the reason why, and we then verified this appropriately, that when we use an identity transformation or a logistic function transformation, the 10H or just even 0, just shortcuts, right? You see that the best of the examples is exactly the identity, and we can explain it in terms of mutual information. All right, so there are more slides that I'm not going to talk about, so let me conclude. So what I try to show to you is now we have the tools to do estimation of entropy and mutual information directly from samples for machine learning problems. We tested this up to 1,000 dimensions with very good results. So that means that we have now the tools to try to probe in the learning of machine learning algorithms with a much more powerful tool than what we have currently. And so I'm going to just stop here. Thank you very much for your attention.